showed that A plus and minus were raising and lowering operators, which raised and lowered the eigenvalues of n. So this is an operator whose eigenvalues are 1, 0, start with 0, no negative ones, 0, 1, 2, 3, dot, dot, dot. Finally, not finally, but moreover, the Hamiltonian is equal to omega. Now, I have left out h bar. I'm going to leave it out, but then I'm just going to show you where it goes. If we leave out h bar, the Hamiltonian is just omega times n. Now, where does that come from? If you multiply A plus times A minus, clearly you get something which looks like this. There's a 2 downstairs, that's this 2, and there's an omega downstairs. That's why I have to compensate it with an omega here, omega n. But quantum mechanically, there's a little correction, and the correction comes because the A plus and A minus don't commute, and that gave us an n plus 1/2. The 1/2 is called the ground state energy, or the well, if it was a field theory, we would call it the vacuum energy. If it is a simple harmonic oscillator, we call it either the 0-point energy or the ground state energy. And it's really a consequence of the uncertainty principle that you can't have both P and X simultaneously being 0. And since the Hamiltonian involves p squared plus x squared, there's no way they can cancel each other. So there's always going to be a residual bit of ground state energy there. You don't lose very much if you just cross it out and forget it, because an additive constant in the energy of a system really doesn't change its equations of motion. So you can ignore it, but it is there for some purposes. All right, what I wanted to do was to show you, is there anything else? Yeah, there's one other important point, that equation that went into showing that the A pluses and A minuses were raising and lowering operators. It was the commutation relations of the A plus and A minus. Dirac's rule, whenever you see two things, commute them. Right. Sometimes, of course, you get garbage. But the commutators are A minus with A plus, just equal to 1. Had I not put the square roots of 2 omegas down there, the commutator would have been something a little messier. And so really the reason for dividing by square root of 2 omega here was to get rid of anything on the right-hand side to divide it away. This commutation relation, together with the definition of n, tells you that n is quantized in integers, and the connection with the Hamiltonian is such that the Hamiltonian or the energy levels are these. Yeah. Yeah. Why it stops at 0? Oh, why 0 is included. Okay, we're going to do it. Yeah. Okay. What we're going to do is we're going to demonstrate explicitly what the ground state is. That there is a ground state, and we'll find the ground state by actually solving the Schrodinger equation. And we'll see that there definitely is a state with 0. So, what is a wave function? A wave function in this context, let's just put parallel to this very tricky and clever operator construction here. Let's write down the wave function description of the same thing. State vectors are replaced by wave functions, which are functions of position. If we're talking about energy eigenstates, we could label the wave functions with a little n down here, indicating which integer they correspond to. The ground state, for example, will be psi 0. Well, the first excited state would be psi 1, and so forth. So state vectors become wave functions. Operators, x, the operator x becomes just multiplication by the coordinate x. I'm trying to remember to use capital letters for operators and lowercase letters for just numbers. Okay, the momentum is replaced by minus I, e by the derivative with respect to x. Again, there's an h bar in there if you want to keep track of h bars. Oh, if you still want to keep track of h bars, here's where it goes, right? And that's the only place. That's the only place where you have to modify what I've done here. Yeah, I guess maybe also here we want to put an h bar downstairs here, I think. But and you can always figure out where the h bars go by using dimensional analysis. Using dimensional analysis and remembering units of h bar will tell you uniquely where to put the h bars. Okay, so there's momentum. And let's check and see if there is a solution of the equation a minus on psi is equal to 0. In other words, is there a state? You know, I can answer your question faster without. Let me answer your question quickly without then come back to calculating. We know that there has to be a state, which is the bottom state. We can't keep going down and down and down for the simple reason that the Hamiltonian is positive. It's p squared plus x squared. P squared plus omega squared x squared. An operator like that has no negative eigenvalues. Just as classically it's either positive or 0, quantum mechanically it also can't be negative. And so there's got to be a bottom. There's got to be a floor to the power of energy levels. Okay. How can we have a floor? The only way we can have a floor is if the bottom state, let's call it O, let's call it ground state, is annihilated by the annihilated means that you get 0 when you hit it with A minus. If you didn't get 0, whatever you got on the right-hand side would be a state of 1 unit lower energy. There is no state with 1 unit lower energy. The only way for that to happen is for this to just give 0. Now, once we know that A minus on O gives 0, then we can look at N. So let's look at N now. What does N do when it hits the bottom state? Well, it is by definition A plus A minus on O, but we already know that A minus on O gives 0, so this is 0. It's an eigenvector of N with 0 eigenvalue. So there must be an the bottom state has to have 0 value of N. That's an abstract argument, but yeah.
So if 0 is an eigenvector, then should there be an eigenvector of 0 on the far right-hand side?
Wait. This 0 here, this state, and this are two different things. That's the eigenvector, and it's normalized to 1. And it's not 0 in any sense. It's just that its name is 0. You know, if I call my friend Art here 0, that wouldn't mean Art wasn't here or didn't exist. It would just mean being unpleasant. I'm calling him 0. Yeah, you can write 0 as a ket, but you have to understand it's not this 0. It's just 0.
So 0 times is...
That answers my question.
0 times anything is 0, so you can write...
Then it's a vector on the left-hand and right-hand side, so you can put the vector in there and it's just a 0 vector.
Thank you.
Yeah, but you must not call it this vector. Whatever name you give it, you've got to give it some... And the tradition is just not to write it as a vector, but just to call it 0. In the abstract theory of vector spaces, you introduce a vector called 0, and it's sort of special. It's the only one that doesn't have a ket sign. But as you say, it is just another vector, a rather special one. Okay.